So we study how supermassive stars die at the end of their lifetimes. So I'm talking about a supernova event. That's the name for... So stars go through a series of nuclear fusion burning stages where they take lighter nuclei and fuse them into heavier. Okay. Hydrogen into helium, that's what our sun is doing right now. And helium, there's a set of reactions that lead all the way up to iron. In the most supermassive stars, iron, you can get to iron and then you're done. Because once you get to iron, it's no longer energetically favorable to create the next element in the series. And yet they exist. There's gold, see some gold over here. There's aluminum, there's uranium floating around. Where do those elements come from? That's a big open question in astrophysics. And one candidate site for the creation of these elements is the death throes of these supermassive stars. When a star dies, the innermost region of it collapses to a compact object, neutron star or a black hole. Okay. But in the process, the outer layers are blown away in what we call a supernova envelope. Oops, microphone needs to stay here, sorry. And that envelope is a candidate site for the creation of these elements. And we are asking, well, what would the recipe have to be in that cloud for this indeed to be where that synthesis, that nucleosynthesis takes place? And the technique we use to probe this, it's called an inference. That's an umbrella term for harnessing information in available measurements to complete the picture of where those measurements came from. Machine learning is a type of inference procedure. Okay. Machine learning relies on extremely large, dense data sets. We're on the opposite extreme where our available data are very sparse because these explosions come from very far away and we have very sparse evidence of them here. So what we're doing is asking how much can we squeeze out of these measurements to predict backwards to where these measurements came from. And by measurements, I'm talking about neutrinos. These are ghost-like elementary particles. Okay. Hold up your hand. Count to 1. There you go, 1. While you were counting to 1, about 1 trillion or 10 trillion or so neutrinos just passed through your hand.
Wow.
They're very hard to capture. Same through the Earth's core, actually. Earth's core is nothing for a neutrino. They're very weakly interacting. They're very hard to capture. And there exist neutrino detectors on Earth, and we are working to ask, well, how much information is contained in what we call the neutrino, what kind of signature is contained in the neutrino measurements at Earth about where these guys came from. Wow. So can we infer the physics of the supernova based on these measurements in conjunction with optical and electromagnetic spectrum observations and gravitational wave observations too? I can go into that, but I think I might be sidetracking us a bit.
So
this is a very long, detailed answer to your question.
So we have the neutrinos, which are they smaller than atoms?
Yes.
Okay.
Oh, yes. Much smaller than the constituents of atoms. So you got an atom, then you got a nucleus of an atom, okay, which takes up a very, very small part of the atom. Wish I had 2 hands.
And here, use my hand.
Okay, well, all right, great. So here's the nucleus. And the electrons orbit the atom, which basically sets the radius of the atom. And to scale it, you would not be able to fit the electron orbital inside this room.
Wow.
And a neutrino is, so within the nucleus now, you've got neutrons and protons inside the nucleus. And a neutrino is orders of magnitude, that is factors of 10, smaller than either of those 2 little guys.
So these are really, really tiny.
Pretty tiny. Yeah.
How do they, so if we have a star that burns out, how in the first place were we able to capture the neutrinos?
So we can't capture a neutrino per se. What we do is we build a physical model of how neutrinos interact with other particles in the vicinity.
Okay.
And what we're observing is evidence that a neutrino has happened by.
So it's like observing behaviors or what happens to other things
Yes.
that we. Okay.
Yes, exactly.
Wow.
Exactly. These neutrino detectors, they're huge tanks of heavy water. I won't go into what that means, but let's just say water.
Okay.
And if a neutrino comes in, well, we're talking many in order to be able to see the effect. There's a characteristic kind of radiation that is given off during the interaction that this detector is set up to be able to capture.
Okay.
So if you detect that characteristic signature in the radiation, then you infer, okay, it is more probable than not that a neutrino is responsible for
Okay.
that signature, for that signal.